السلام عليكم ورحمة الله. كيف أنتم؟ كيف أصبحتم؟ كيف أمسيتم؟ أخوكم الدكتور رمزي بن أسامة الحلبي يحاضركم للمرة الثانية، ونسأل الله تعالى ألا تكون الأخيرة. This session will be entitled Statistical Inference. يعني طبعا هي متعلقة بالstatistics وفي مسألة وهي الانفرنس، وهي عادة تكون من باب التوقع predictions. فتكلمنا عن probability في المجلس الماضي وهو علم الاحتمال. الآن عندنا inference, which is if you have certain properties, if you have certain parameters, if you have certain variables that you need to predict, can you predict this based on previous values? Can you predict this based on current values? فكيفية توقع بعض المسائل، توقع ماذا ستكون هذه المتغيرات، ماذا ستصبح، هذا الذي سوف نشرحه بإذن الله تعالى. Firstly, we're going to start with joint, conditional, and marginal probability. يعني حيكون مثل تذكرة عن probability اللي شرحناها في المرة الماضية، وذكرنا joint probability, conditional probability, and marginal. نرجع نعرج عليها بشكل يسير، ثم نبني على هذا لنشرح مسألة statistical inference. Then we have probabilistic states and the Markov chain. Then we have statistical inference, likelihood, so the concept of likelihood, and what's the difference between likelihood and probability, maximum likelihood, Bayesian inference, and finally Bayesian updating continuous priors. So let's begin. This is a reminder of the sets. فنحن لما نقول probability sets, it means that you have one or more, usually it's more than one set. And then if these sets intersect, we call this union or intersection of the sets. And we might have complements of sets, which is everything beside the set. We have the symmetric difference of two sets, which is everything but the intersection of these two sets. And we discussed this in the last session. فهذه المسائل المهمة نرجع دائما نعيدها، إنه إذا في عنا two sets or more, these sets eventually will interact at some point. حيصير في عنا مثل ترابط. هذا الترابط المفروض نفهم نحن إنه ممكن يكون في جمع ما بين السيتس، ممكن يكون في exclusivity، يعني الست الأول is completely exclusive from set 2 or set B. And this is manifested through calculations as well. And I told you before that this is called the Venn diagram. فنحن حتى بالمسائل الحياتية الآن إذا عنا هذا الكونسبت بعقلنا، عشان هيك بتلاقوا دائما البروجرامرز والساينتست والانجينيرز حتى بالحياة طريقة تفكيرهم مختلفة عن غيرهم، لأنه دائما نتخيل الأمور جرافيكلي، عنا الجرافيكال aspect of things. And this is important in your life. If you have multiple events that intersect and you want to see where a certain variable fits, you can do this. What is joint probability? It's the probability of event Y occurring at the same time that event X occurs. يعني تداخل، عندنا تداخل ما بين event X و event Y. So what is the probability؟ ما احتمال حصول event X في الوقت ذاته أو في الوقت عينه الذي حصل فيه أو يحصل فيه event Y. ف two events are occurring. If they occur at the same time, يعني event مثلا to pick, or let's say an event that someone is standing and another event that someone is sitting. Can these two have a joint probability, standing and sitting at the same time? ممكن يكون في عنا event that is standing, the other event is drinking water. So now, can we compute the joint probability, which is standing and drinking at the same time? So this is B A inter B, which is the joint probability between events A and B. Conditional probability, and I told you about this, and we discussed a very important rule that we will base a lot of things on today, which is Bayesian probability or Bayesian rule. Conditional means that you have B, which is an event, and then you want to build another event based on it. So if B happened, what's the probability that A happens given that B happened? يعني الآن عم نبني احتمال على احتمال. إذا حصل الأمر المعين، ما احتمال أن يحصل الأمر الآخر بناء عليه؟ وذكرت لكم أكثر من مثال. So it's basically the probability of A inter B, which is what we just saw, joint probability, divided by the single probability, or we call it the marginal probability of B, which is the event that already happened. So now I'm going to introduce these concepts. This is called conditional probability. P of A at condition that B happened. This is called the joint probability, and this is called marginal probability. So if you have two, you can compute the third one, and so on. Now we go into another point, which is probability states. States هي الحال. يعني شو حال الايفنت، او شو حال الشخص، او شو حال الانتيتي that we are studying. In what state is it؟ اللي دارس logic design or discrete math بيعرف هذا الموضوع كتير منيح. نحن we have states، او حتى بالindustrial automation. In any case, you have states like, let's say, on and off. And then your device is continuously jumping from state to the other. يعني هلا أنا التي في داير، كبست كبسة على الريموت عملت ايفنت معين، كبست كبسة الأوف طفى، رجعت كبست أوف ضل أوف، رجعت كبست كبسة جديدة ضوى. So you are controlling the sequence of action that is controlling the states of that device or that element. These probability states are called the Markov chain. So as you can see over here, I'm going to be varying these and varying the speed over here. This is event A and this is B. So you have a chance that A will always remain in A, it will loop. يعني إنسان واقف حيضل واقف، وهون sitting ممكن يقعد ياخذ قرار إنه يقعد، وممكن يضل واقف. So you have two cases, two states that you are continuously changing. This is a two-event or a two-state, let's say, two-state Markov chain. It can, of course, get more complicated, and you will have a probability of either staying in your state or going to the other state. And this, in turn, also depends on other variables. فأنت الآن بحال معينة وعندك احتمالان، إما أن تبقى في الحال التي أنت عليها أو أن تنتقل إلى حال أخرى. Now, this is an example of me varying the actual probabilities. So this is how you represent this. It's actually memoryless. So when we say memoryless, it means that it doesn't know anything about the past. It just knows about the current state and computes the probability of the next state. So you have A and B, state A, state B, state A, state B. It's like a state table. And then you are either going from state A to state B or remaining in state A. So let's see this. I'm going to be varying the probabilities. So probability of A staying A at A is very high. So it's going to keep looping over here. When it decreases, eventually the probability that it's B right now and it was A, it means that it's now higher. So I'm going to pause this and explain. You are at A. What's the probability that you will remain at A? So now you're at A. What's the probability to remain at A? If it's low, logically speaking, the probability of getting to B is higher because these are complements. So it's going to be always one in a single row. Similarly for A knowing B. If you're at B and the probability of going to A is 0.05, which is 5%, there's a 95% chance that you will remain in place. So this is basically it now. Going from A to B and having different probabilities. So now let's start discussing another point, which is classical inference. But first, let's define a few things. What's a statistic? A statistic is anything that can be computed from the collected data. يعني الآن أنا في عندي signals, EEG signals, or a bold MRI signals. You will learn about this hopefully when you go deeply into computational neuroscience. A statistic is anything that you can compute from these signals that I just told you about. It can be the mean, it can be the variance, it can be the maximum, it can be the mode, it can be the median, and so on. So it's either a point statistic, which is a single value like the mean and standard deviation, or it can be an interval statistic or range statistic, which is like the interquartile range between the 25th and the 75th percentile. So it might be the IQR, it might be the standard deviation. Usually we say mean plus minus standard deviation. This is range statistics. Or we can say median plus minus the IQR. Or we just give the IQR in parentheses. So a statistic itself is a random variable. I told you about random variables last time. Random variable معناتها نحن عندنا points. هدول البوينتس نحن ما نعرف exactly what the value will be, but we can expect it. We can have an expected value or a mean. And this is based on probability and based on the model, based on the previous values, and so on. This is what we're doing actually. It's very important. نفهم نحن ليش عم نجمع the probability مع statistics. What's happening is that you have data that you are collecting right now. أنا هلا عم بعمل recording لتخطيط الدماغ. عم بعرف أنا قديش كم مايكرو فولت هلا عم بيصير عندي at this exact point in the brain. Can I expect what will the value be in 1 millisecond, 2 milliseconds? Can I build a model based on it? Can I do some statistical analysis and predictions and inferences based on what I know? This is very, very important in this field and in other fields. So now classical inference, you have a database of EEG, تخطيط الدماغ, signals, من region معينة كرمال ما كتير نوسع. And then we assume that this activity is Gaussian. Remember in the last session, فرجيتكم أنا كيف لما تكتر السامبles it will end up being Gaussian if it's standardized. وفرجيتكم كيف signals based on the kurtosis, skewness, and statistical parameters, we can know the stage of sleep, rapid eye movement, and so on. So imagine that you have hundreds of signals, and then it turned out to be Gaussian and normally distributed, يعني bell-shaped, across the trials. لأنه usually in neuroscience we don't do just one trial, نعمل أوقات 1000 تنشوف ال evoked potential or the response that is happening in the brain. And then I ask, what's the mean and standard deviation that gave rise to that EEG signal? So ركزوا كتير منيح على النقطة لنفهم شو البوينت من inference. You have observations, you have data. You want to predict or expect or perform inference on the mean and standard deviation that gave rise to that data that you have. So you have data and you are computing the probability that of the mean or standard deviation or any statistic that gave rise to the data that you have. So the prior is the data. You have the data with you, and you are trying to do some assumptions and predictions on what were the parameters, statistical parameters that gave rise to the data that you are seeing. And this can be modeled as such. You have the data points, okay? You want to calculate which were the values of mu, or mean, and standard deviation that gave rise to the data that you have. Knowing that it's a normal distribution, you have this point, and you have the mean and standard deviation. The mean, expected mean, you know how to get it. It's summation of values divided by number of samples. And you know how to get the variance and standard deviation, which is the spread around the mean. Now you just computed what we call the likelihood. So please be careful. There's a difference between probability and likelihood. Likelihood is probability of data knowing P. So it takes the data as fixed and computes the probability of the data for a given P. So if I know the mean and variance, let's say, it's a given, and you have your data, you can compute the likelihood. So what's the likelihood of the mean to be this much, the variance to be this much, knowing that my data has these values and these parameters? Now, how do you estimate this? You have multiple algorithms to estimate the likelihood. It's all based on probability and optimization. Probability, we already discussed this. Optimization is the fact or the process of maximizing or minimizing. Usually you maximize a certain value that you need to be high, or you minimize a cost function, which is the error. So basically you're minimizing errors and differences to get to the optimal point, or you are maximizing a certain score. One of the algorithms that is very famous is the MLE, which is the maximum likelihood estimate. So it's the value of, so it's getting the value of P that maximizes the likelihood. This is what we just explained in the previous slides. Argmax means what is the maximum value, okay? Argmax. So it's an argument and it's the maximum value of it. So when we do this, it's called optimization. You are optimizing a certain parameter in order to achieve a certain condition or a certain known parameter. This is the whole concept. But then, can we use maximum likelihood everywhere? No, you can't. ما فينا دائما نقول maximum likelihood. It depends on the set of problems or the problem that you have. So please be careful now. There's a difference between probability and likelihood. Probability is not where you have data and then you are estimating values of certain parameters. Likelihood, on the other side, or on the other hand, is having data and then performing some kind of inferences to estimate values of a parameter of interest. So in one case you have data, and the other case not necessarily. Now, Bayesian inference, it's easy. I explained Bayesian rules last time, and I gave you a briefing today, and I just explained inference. فالآن صار في عندنا نحن شغلتين. Bayesian, which is computing priors and computing posterior probability based on prior probability and based on probability of certain events. And we know that inference is trying to predict. So now for Bayesian inference, we are not focusing on the likelihood function, but instead we are focusing on the posterior distribution. So now you have a few terms. صار في عنا the posterior distribution وعنا the prior distribution. Okay, so posterior يعني ماذا سيأتي، وprior معناتها ما الذي حصل. ما هو الشيء الذي عندنا؟ هذا اسمه الprior. We know it for sure. The posterior distribution is when you are trying to predict or expect a certain a future value based on what you have. So what is the probability of y knowing x? It's the probability of x knowing y times probability of y over px. It's exactly the Bayes rule that I showed you last time. But now we are doing this using data and trying to do inference on certain parameters. So it's the context that varied, but it's still the same concept. So now, if you want to put this into a nice frame of analysis, you will have a table and you will have graphs. So Bayesian updating using continuous priors, you will have a hypothesis for a certain parameter. You have a prior, you have a likelihood, you have a Bayes or Bayes numerator, and the posterior. So now you have a prior, you have a likelihood, and you want to get the posterior. So let's suppose that you have a certain distribution or certain data, which is the blue one, and you have the data that you are collecting right now. You can get the posterior, which is the next value in purple. Okay, so that's very important. I have the model or the actual probability or model of the EEG data at a certain time, and then I collect data right now. Based on this, I can build a certain model to be able to do inference and expect what would be the shape of the data in a posterior manner. So you have data and you have a model that you pre-built. You can expect new values based on it. So this is basically it. شكرا جزيلا، جزاكم الله خيرا. وإن كانت الأمور غير واضحة إن شاء الله سيكون لنا solving sessions. TAs مشكورين، يعني عم بيقوموا بواجبهم وزيادة وعم بيشرحوا لكم ال practical aspect of these. So please make sure that you watch or attend the practical sessions. لأنه eventually this kind of sciences or of science disciplines is not purely theoretical. ما بينفع انه دائما نضل نظريين. لازم دائما انه نتبع العلم النظري بتطبيقات practical implementations, and the best way to do this is via programming simulations. فيكم تستعملوا R، فيكم تستعملوا Python, all kinds of languages. شكرا جزيلا وبارك الله بكم ونفع بعلمكم. السلام عليكم ورحمة الله.